When you look at Earth, one of the most startling things you see as opposed to the other worlds is it's blue with white clouds. And that's all water. No other world in the solar system has this much water on its surface. Certainly not liquid water. There are some moons that are covered in ice, but not in liquid water. So Earth is unique in having all this liquid water. In fact, what makes Earth very special is the temperature and pressure on Earth are very close to what's known as the triple point of water. Triple point in chemistry is the temperature and pressure that allows something to be simultaneously solid, liquid, or gas. Since the temperature and pressure on Earth is just very tiny bit off of that, that means small variations in temperature and pressure can cause water to be solid, liquid, or gas. And so that's why we get ice, we get snow, we get water, we get water vapor, we get clouds, we get all kinds of things here that can happen here. Now, clouds are not water vapor, they're actually condensates, but we have water vapor in the atmosphere. And so very small changes in temperature and pressure can make the water vapor in the atmosphere come out of the atmosphere in the form of rain or snow. Or it can make the water on the surface that is water, liquid water, or even snow, go back into a gaseous state. Water will evaporate. Snow will sublimate. Even if it doesn't warm up above freezing, snow can dissipate off the ground by going straight back into a gas. And so the fact that there's all this water is the hydrosphere of the Earth, and we want to talk about that. In fact, when we look at Earth, again, the startling thing is all this water. 71% of the Earth's surface is covered in oceans. That's a lot of water right there. About half, over half, in fact, are deeper than 3 kilometers. 3 kilometers is almost 10,000 feet deep. So much of this ocean water is extremely deep water. Now, the interesting thing is that over half is more than that, but 45%, just under half, is less than 200 meters deep. So that means that the oceans are going to be normally either very deep or not so deep. That gives rise to the idea of the continental shelf, which we'll talk about later. So it's either deep or not. That's a lot of water. But if you congregate it all in one spot, it would make a sphere only 860 miles across. So this graphic right here shows what Earth would look like if you put all the water in one spot. And now all of a sudden, this doesn't seem like a lot of water. Remember, the Earth is about 12,500 or so kilometers across, but the oceans are only a few kilometers thick at the deepest. So that even though this looks like a lot of water, it's all spread out along the surface, but it's really a very small layer right there. Now, it's very important to us, but this is really not that much water. Earth is basically a rock. We got all this water on it, but the water is a very small percentage of the planet, and we are mostly rock. This is a rock world that just has a little bit of water and a little bit of air on it, because the atmosphere itself is not very much. You can take all the air here and convert it into a liquid, and the entire atmosphere would just be only an inch or so deep. So there's very little stuff here that's not rock. It's just the stuff that's not rock is so vitally important to life. Well, again, if you imagine here that we collect all the water on the Earth right here, there it is to scale. Okay, so there's Earth, there's all the water to scale. Most of it is salt water. All the fresh water on the entire planet, and that's what we need as humans, okay, is going to be even less. Fresh water is actually very, very rare on Earth. And that's the part that's so important for humans. And that's why, you know, some sociologists and so forth, you know, think there's the possibility in the future of wars over water. In fact, there have been wars fought over water, availability of water, particularly in some of the more arid parts of the world. Because that fresh water is so vital for life. You can't drink salt water. Though we do have technology now to actually take the salt out of the water and make it fresh water, but that process involves using energy, and typically if you use energy, there's an environmental penalty to pay for that. You end up polluting things. The hydrosphere, less than 2% of all the water on Earth is fresh water. The average salinity is 35 parts per trillion. Okay, what causes all this salt? The salt is mainly stuff in the minerals that's on the land that's being dissolved by water. Okay, remember, water is near the triple point. So it evaporates, becomes water vapor, and then it rains. And that water falling on the earth then, as it's working its way through the rocks, actually dissolves some minerals. Now, when the water evaporates, it leaves those minerals behind. So the oceans, that's where the water tends to go to. It evaporates and it gets salty. Now, in some arid parts of the world, the water doesn't get a chance to get out to the ocean. It just congregates in a big pool and then evaporates. The Dead Sea, for example, a place where the water is running into but it's not running out, and so over time it just gets more and more salty. It's only so big, and so that means that the rivers that run into it and the salt that's left there does not get a chance to dissipate among all the rest of the water, like the water that goes to the oceans. Same thing with the Great Salt Lake in Utah. Water flows into it, but it doesn't flow out. It just evaporates and leaves behind the salt. And so it just gradually gets saltier over time. In fact, both the Dead Sea and the Great Salt Lake are getting even saltier over time, much more rapidly due to human interaction than it used to, because they're actually pumping some of the water out and taking the salt out of it in order to use the fresh water. And so that makes what's left even saltier and saltier. So we've actually interrupted the natural salt balance even in those bodies of water. The water cycle, water evaporates, okay, goes into water vapor. Something disrupts it, the temperature and pressure gets just slightly off, it condenses into water droplets or into ice crystals, and those give you clouds. Whether it's water droplet or ice crystal, they can both be a cloud. Cirrus clouds are ice crystals, whereas the cumulus clouds are typically water droplets. When the water droplets bump into each other, they get bigger. If they get big enough, or if the ice crystals get big enough, then atmospheric circulation can't keep it up and gravity makes it fall. And so when that happens, you get rain. Hits the ground, a lot of it runs off along the surface, some of it works its way deep underground, and there's layers underground here where it's very rich in water, and that also will flow in the general direction of downhill, okay? And so if you dig, for example, you drill a well on Earth here, if you drill low enough, you get to the saturated layer of rock down here, and now you can pump water up, okay? And so that's how water wells work. So this is the water cycle. Solid, liquid, or gas, it's all water.